Okay, so good morning, everyone. Welcome to this meetup of CLIQ-ai. And today we have the pleasure to have two presentations. One is by Bang Liu and another one by Sébastien Paquet. Bang Liu will talk about the foundation models for agents, and he recently led a project of a survey, a long survey paper about the agents. And today he's going to talk about agents and the foundations of agents. Uh, and Bang is assistant professor and very soon associate professor at University of Montreal. He's a CFA chair on AI. He's also associate member of Mila. He's working on a lot of different projects on NLP and AI for science and so on. He's also a member of Institut Courtois. And Sébastien Paquet is a VP of COVEO. He's going to talk about the industrial application of agents. I will do the presentation of Sébastien a little bit later. So let's start with the presentation of Bang.
Thank you very much, Jamie, for the introduction. So I will share my screen. Okay, let me. Can you see the slides?
Yes.
Okay. Let me make it full screen. Okay. Yeah. So let me minimize the window.
Yeah. Good.
So yeah. Good morning, everyone. So it's my pleasure to present this topic here. So the title is Foundation Agents and Agentic Memory System. So as Jamie mentioned, so we worked on a long survey recently, which is about the AI agents, especially based on large language models. So I cannot cover every topic like in the long survey. So I will mainly introduce the concept and the framework of foundation agents and emphasize on the memory part, especially one of our recent research on memory network. So let's start from like what is foundation agents? So historically, like there are many myths and concepts of AI. So in the Tales of Greek, we have bronze automation from Greek mythology built by Hephaestus to protect Crete. So you can see that this is a huge bronze robot, which is people built to defend their home. And in the middle, it is the Leonardo da Vinci's humanoid robot, which is an earlier mechanical automation designed to mimic human motion. And the right figure is like the paper from Alan Turing, so which is computing machinery and intelligence. In this paper, he proposed the fundamental question: can machines think? So we can see that AI has long been driven by humanity's ambition to create entities that mirror human intelligence. So maybe the most simple and fundamental question is, what is an AI agent? So if you check the textbook from for AI, like from the University of Berkeley, so you will see a definition which is similar to like just saying agents continuously perceive, decide, and act automatically. And this figure is from, I think it's from the Dr. Wu Lilian's blog, which shows that if you have a large language model and you combine it with different modules like memory, planning, tools, and actions, actually you formed a very basic setup of LM agents. So traditionally, many agents are built on rule-based or domain-specific rules. And with LM's strong reasoning and language understanding capability, LM-powered agents have natural language fluency, has broad reasoning capability, and dynamic adaptability to different tasks and environments. And of course, this figure just shows a very simple setup of agents, and people have developed different types of architectures and workflows for different agents. So the motivation for us to conduct a deep and broad survey about the research of agentic AI is, first, we want to know where are we nowadays in AI research today. So we have powerful language models, we have impressive reasoning capabilities, but we still have limitations in AI safety, the controllability, reliability, and trustworthiness of AI, which are all very important topics. And we further want to know what can be improved. So first, we want to have a unified framework to describe what is an AI agent and how we can measure the progress of research in the different parts of AI agents. So we also want to check the modularity, the safety, lifelong learning, emotion grounding, and many other topics surrounded with LM and AI agents. So we tackle this question by connecting AI with humans and society. So we want to draw insights from human brain functions and social behavior, and like our brain is the only intelligent things we know in the world. And just like said, like what we cannot create, I cannot understand. For AI research, it's more like what we cannot understand. We need to be very careful to create because it's like hard to control if it's very powerful. So we want to identify the gaps by comparing human cognition and AI agents, and we want to develop human-centered, socially beneficial AI. So in this case, making connections between human brain and society with the development of AI is helpful. And we want to foster human-AI collaboration, transparency, and trustworthiness. So in this figure, this table, so this is a very short one. You can have a glance about like what's the difference between human brain and LM agents. So for example, from the hardware level, one is very energy efficient. For example, our biological brain is very energy efficient. But for LM and LM agents, they are built on large-scale GPUs, a lot of data. So of course, it's quite energy intensive. And for consciousness, our human beings are genuinely subjective and experienced. And we can say that nowadays, I think it's still safe to say LMs are not conscious. And for learning style, human beings are naturally strong in perform lifelong learning, continual learning, and adaptive to different tasks, but it's relatively challenged for neural network models. And humans are very creative and emotionally, socially grounded, but it's not that case for LM agents. And we also checked the capabilities like owned by human brains, and we want to see how it is developed, being researched by different researchers. So we generally we grossly categorize different capabilities in 3 levels. Well, L1, the green color, means it's kind of well developed in the current AI research, and L2 is kind of moderately explored with partial progress. And L3, the pink ones are really explored or significant room for research. So for example, nowadays we can see our neural network models has already been very strong in language comprehension and visual perception and so on. And for many important topics, like let's say the decision making, logical reasoning, planning, working memory, attention, and so on, although we still have a lot of research about them, but there's still a large room to improve. And there are also many like topics which are really explored, like the emotional processing, the empathy, self-awareness, and cognitive timing and predictive modeling and so on. So the reason we want to map and compare the different functionalities like owned by human brain and AI, we're not trying to say that we need to mimic every feature of human brain. Instead, we just want to make a comparison between them and get inspiration by like knowing better about these gaps. Because we know like there are also many advantages of LMs. For example, they have very large knowledge capacity where it can learn from like a lot of data which like cannot cover by human brain and so on. Another challenge is that we still lack a unified framework. So the current AI agents often built in ad hoc manner. They are kind of fragmented because like people in developing different agents by combining different parts of the modules, like they have designed different types of memories and they have different reasoning mechanism, and some of them equipped with some advanced action libraries and so on. So we lack seamless integration of perception, memory, reasoning, action, and different modules. But human brains has integrated yet modular approach served as an inspiration. So we want to know what is a good modeling of different AI agent functionalities. So this is the table of notation. So we don't need to remember all of that. So let's check the figure directly. So basically, this figure shows an agent loop. So at the first glance, it's kind of similar to like what we will see in a reinforcement learning textbook, where you have an agent, it perceives the environment and making decisions to have some action in the environment. So here we emphasize on the internal mental states and how different paths are contained in the cognition process. So specifically, so let's start from the environment. Well, the environment has a state space S. Well, at time step t, you will perceive the environment state S of t. And then you have sensors to turn the environment state into your observation O of t. And based on the O of t, you need to have a cognition process to understand and making decisions. So specifically, we modeling the cognition process into two parts. The first part is about learning, where we think learning is based on the current observation and past experience. You're updating your mental states. So here we have different types of mental states. For example, world modeling, the reward, memory module, your goal, your emotion status, and so on. So there are kind of sub mental states, and different agent designs actually utilized part of them. And then, based on the updated mental state, you can reason about what actions to take at the current status, so which produced A of t. And this action is still the thought from your brain. And then you need to execute this action. That's why we have an execution where you got E of t. So formally speaking, this is the definition of the agent loop. So you have the current state of the world, and you have the perception function P, and based on the current state S of t and the last mental state mt minus 1, you got the current observation of t. And then based on the current observation, you need to learn and reason about the actions. So the learning is based on the previous mental state mt minus 1 and your last action at minus 1 and your current observation of t. You will update your mental state. So your mental state transit from mt minus 1 to mt. And then based on your mental state, you will reason about what actions to take. So this is your reasoning function. L of t equals to the reason function given m of t. And then you will execute this action. So here actions can be it can be a pure mental action. For example, you're planning about your future actions. It can also be a physical action you can execute with different tools like APIs or a tool in the physical world. And based on the action execution, you will have impact on the environment. So the environment will transit from the current state S of t to the next state S of t plus 1. So until now, we have defined what is an agent loop looks like. So what is an foundation agent? So this long definition is what we provided in our current survey paper. But after that, we further consider, can we make it more concise? So basically, what we want to express is a foundation agent is a fundamental intelligent unit with universal understanding, cognition, and action capabilities that can be operate in any environment and collaborate to form collective intelligence. So actually here we are emphasizing on two parts. The first part is it is a universal design of the agent, which means it can be generalized to different types of tasks and environments. And the second is it can be formed into a multi-agent system so that it can collaboratively solve different tasks. So the key capabilities a foundation agent should have includes the multimodal perception, the cognitive adaptation, goal-oriented reasoning, purposeful action, and multi-agent collaboration. So all of this makes them can be adapted to any types of tasks and environments, and also enable them to collaborate with each other to form small-scale or society-scale agent groups. And we also made connections to existing theories. For example, the classical perception, cognition, action cycle, we're consistent with that, and we extended with more explicit internal mental states and different modules. And if we compare with Minsky's Society of Mind, we have modular cognitive subsystems like memory, emotion, reasoning, and so on. And if we compare with the Bozaki's inside-outside perspective, which is mainly saying that instead of think our brain is passively percept the environment and making decisions about the actions, we actually actively perceive the environment and keep acting. So here we have internal mental states which actively shape the perception. And if we compare with the POMDP framework, we emphasize the internal mental states and the active learning and reasoning process. And if we compare with Bayesian active inference, we minimize the prediction error via updated mental models. So basically, we want to say that compared with existing theories, we are consistent with them and we're actually more comprehensive. And actually, we're tackling the agent from different perspectives. So the core components of the agents. So let's start from the cognitive core. So basically, it's the central executive that orchestrates the reasoning, planning, and reflection, and many other mental processes. So here, as we have shown in the previous definition, the learning and the reasoning capability are the core functionalities of cognition. So for learning, we have different types of learning, right? For example, supervised, unsupervised, self-directed learning, reinforced learning, and so on. And for reasoning, here we classify them as structured reasoning and unstructured reasoning. So for example, we have chain of thought, tree of thought, graph of thought, and so on. Basically, they are kind of we are modeling the reasoning process with some kind of data structure. And we are managing the complexity and try to maximize the efficiency by searching through the action space. And for unstructured reasoning, so it's more about decision-making, sequential decision-making, and we're actually reasoning about the next step based on the local context. And for planning, so we have you can consider it as a more large-scale action, which is deciding what are the nested actions to take in a more long-term plan. And memory system is another key topic we want to highlight today. So human brains has multi-level memory inspired by biology. We have the short-term memory, we have working memory and long-term memories and so on. So the memory system is key to enable continuous learning while avoid catastrophic forgetting. Here the design challenge is how can we balance fast query over vast memories with minimal latency and cost? So in our survey, we actually defined the life cycle of a memory system. So starting from the memory acquisition. So based on the raw observation, the raw data, you're the memory acquisition is about how you can effectively pay attention to the most relevant part of the information and also perform denoising to only preserve the most valuable parts. So it's also about how you can actually tackle with multimodal inputs and better align them, fuse them. And memory encoding is about how you turn your perceived information into your internal representation. And memory derivation is about how you can drive new valuable insights from the observed information. So for example, based on your accumulated, for example, dialogue histories, you can actually infer some new information which is not explicitly mentioned in the dialogue. So this is about using reflection to drive new informations. Another very classical way is just you have some summarization about a long context so that you will have a condensed representation of your information. And after you have derived your memory, you actually distill the information and make the memory more concise. So you can further retrieve and utilize it. So memory retrieval is about how you can effectively find the most relevant part of information based on the current local context. And utilization is about, with the retrieved memory, how you're going to utilize this memory to improve your response, right? In our survey, we also have chapters about the world model. So basically, a world model is the internal representation of the environment's dynamics and the agent's own causal influence. So basically, if you have an internal world model, you can predict the future without actually execute actions in the real world. So basically, you can imagine what will happen if you do some action sequence. So based on the world model's transition function and observation function, we can categorize the existing research about world model into different types. So basically, the transition function is about, given the current world state and action, what is the next world state? And observation function is, given the current world state, what will be your observation? So the implicit world model basically combines the transition function and observation function into a unified model. So basically, you explicitly predict the next observation based on the current ones. And for explicit world model, they will separately model the transition function part and observation function part. And for simulator-based world model, they will have a simulator to simulate what will happen if you have some action. So basically, it is a mimic about the real world, but of course, it will be limited to the accuracy of the simulator. And there are also other hybrid and instruction-driven measures about world models. And the reward or value system, so they provide goal signals that can shape learning and behavior. So based on where the reward signal comes from, we also have different categories of reward systems. So the extrinsic reward. So you will have an external reward evaluator. Well, based on your action and feedback, the reward evaluator will calculate some reward value and give it to the agent. And for intrinsic reward, basically it means that the reward is estimated by the agent itself. For example, it can be by some self-reflection or self-evaluation mechanism. And hybrid reward combines both of them. And hierarchical reward, so you will have reward evaluator and self-evaluation. So basically, the hierarchical reward will decompose a complex task into some sub-objectives so that you can have separated reward in a hierarchical manner. And for emotion, so emotions can act as a first heuristic. So for example, when human beings feel fear, we will avoid to do something. Or when we feel curious, so we may show more interest to explore the surrounding environments. So this is similar for machines or AI. So emotion can serve as motivation supply that sustains internal drive and add robustness and adaptability, but demands tight control to avoid undesirable side effects. So until now, the exploration about AI emotion is less than other paths. For perception system, so the key is how we can model the multimodal input signals, includes the text, the vision signals, audio, and others. And we want to extract salient features and fuse them into a unified scene understanding. So it must run in real time and remain robust to noise and uncertainty. So right now, human beings and AI agents have some overlapping in terms of perception signal types, but they also have their own unique perception signals. And the action system is mainly served to convert the cognition decisions into executable commands. So here we have a figure to show to clarify different concepts sometimes can be confusing. So for example, like you have a cognition system which can produce a sort of action. So here the action produced by the cognition system is still a thought. It is a directive arising from the cognition reasoning. So to actually execute this action in the real world, you need to have an action system to turn your output action thought into executable forms. So the action system can call different tools, where we define tool as callable utilities for specialized execution. And we have APIs, which can serve as a format of a tool. So basically, an API is an interface for programmatically invoking services. And an API includes functions, where function is the atomic unit of implementation by programming. And of course, you can have other type of tools. Format is not in the format of APIs. So for action system, we need to balance the feasibility, the efficiency, and the safety. And how to learn fine-grained skills and operate in continuous action space is a challenge. So you can check this survey paper to know more details. Sorry. So today I will mainly focus on the memory system part. So as we know that human memories is a hierarchical structure. So we have long-term memory, we have sensory memory, also have short-term memory. So for long-term memory, you can further divide it into declarative and non-declarative forms. And for the declarative, you have semantic memory, episodic memory, and many others. So basically, we can say that for the human memory system, it is a multi-tied structure, and you can divide the memory system into more fine-grained categories. So human memory exhibits rich diversity and adaptability. So we mainly discussed the memory representation and the memory life cycle in our survey. So for memory representation, we discussed the different formats like the sensory memory, short-term memory, and long-term memory. We discussed how they are modeled in the existing AI agent systems. For memory life cycle, we discussed the memory acquisition to the encoding, derivation, the retrieval, and utilization. So next, I will introduce our recent research about memory network, which is called RR3MEM. So the motivation is that the existing large language models are stateless, which means that if you have an input to this language model, it will have the output. If you next time you ask it the same input, it may produce the same output because it doesn't have memory about your past experience with the LM itself. Of course, now if you are using ChatGPT, actually it is equipped with a memory system. But if you are using the raw like GPT model, it doesn't have a memory. So we can see that the conventional LLMs process each request independently, and the past experience is not retained, which is like you have brittle long-term reasoning. So if we have external memory, we can make LM stateful. So attachable memory buffers evolving over time and enable continuous dialogue. So with the external memory system, you can enable continuous dialogue and personalized agents. And we can also perform long horizon tasks. So existing memories can divided into explicit or implicit format. So explicit memory includes like the vector database, the document index, classification, and so on. So they are editable, interpretable, but they also need extra latency and storage. For implicit one, like they are the neural network itself, basically the memories are encoded in the model ways. So it's always available. So it's very low latency because you're retrieving the memory during the inference process. But it's also hard to interpret and update. So there is a trade-off about memory retention and retrieval. So if you are using explicit memory in the external media, like you store information in the knowledge base or vector database, so you can retrieve very accurate and original information. So there is high retrieval reliability, but also it requires the storage and the management effort, right? For implicit memory, which is like information stored in the neural network parameters. So for example, you can perform model editing or context integration. So it's easy to store and manage because it's stored in the neural network weight itself. But it's also like the retrieval reliability is like reduced. So in our research, the R3MEM, so we want to develop a memory stored in model parameters while optimizing for external retrieval. We want to like preserve both high retrieval reliability and high storage and management efficiency. So how can we simultaneously maximize the memory retention and retrieval by keeping the external storage minimal? So we have several key ideas. The first idea is consider memory as a compression process. So if you consider memory retention, it's about compressing the long raw context into more condensed memory format. So it feels like a zip process. It provides original long context. We transform it into memory storage. For retrieval, it's like the decompress process on demand. So it's like the unzip. So basically, you can see they form naturally a dual task. So in this case, we want to have a reversible model which can perform these two processes. So the next idea is to utilize a reversible neural network, which is actually if you have a one neural network architecture, but it can infer in two directions. So in this case, you are performing weight sharing, so which enables tight coupling of compression and expansion. So reversible neural network has been a research that existed for a long time. So for example, in this figure, we show that this is from an existing research paper. So you can see this Y1 and Y2 is based on the X1 and X2, as well as two modules, F and G. So Y1 is defined by X1 plus Fx2, and Y2 is equals to X2 plus GY1. And based on F and G, so actually you can also calculate X1 and X2 given Y1 and Y2. So in this case, actually, this is the definition of the RefNet. So you can have the forward path and backward path, where forward path is given X, you calculate Y, and the backward path is given Y, you calculate X. And based on an existing research, the prior research, which utilized an adapter-based reversible block on frozen backbones. Actually, in this paper, the authors propose that you can inject adapter modules to like transformer neural networks so that you can actually turn the original like unidirectional transformer network into reversible architecture. So you can see in this figure, those two adapter, the yellow paths, they are the adapter F and adapter G. By adding these two adapters, actually we can turn the original transformer layer into reversible transformer layer. So in this case, we don't need to train from scratch. Instead, we only train these adapters while keep the original network layers frozen. The next idea is hierarchical compression. So what does this mean? So if you think about it, like usually we have a short query, right? And we need to retrieve a long context as our memory. So it's a short to long retrieval. And let's consider this retrieval as a generation process. So which means based on a short query, we need to generate the original long context. So in this case, we can actually utilize an existing LLM like GPT-4 as an oracle model, which can decompose our documents into like condensed paragraphs and then into sentences and entities. And then we can actually build context query pairs at every level. We have the document to paragraph level, paragraph to sentence level, and sentence to entity level. So basically, you can see the length from the context to query is reducing gradually. And we also utilized a length filter to keep informative segments only. And those multi-granularity pairs fill both compression and retrieval training. So this figure on the right part is the prompt we utilized to ask the GPT-4 to help us generate those multi-granularity context query pairs from the original documents. So in this case, we don't need to manually label like training data by ourselves. Instead, we can ask it to have a compression based on different granularities from the original documents. So based on all the 4 ideas we have mentioned before, we developed the R3 MEM architecture. So on the left part, you can see like we have this training from different granularities from the document level. Well, we then compress it to paragraph level. Then from paragraph, we compress it to sentence level, a sentence entity level. And reversely, from the entity, we can generate the sentence level information. Similarly, from sentence, we generate paragraph length information. And finally, from paragraph query, we generate the document level information. So you can see the key is we are reusing an existing language model so that we don't need to train from scratch. And we're actually utilizing the language capability learned from the pre-training. And the second is we turn the model into a reversible transformer network so that we can generate from short to long as well as from long to short. So we're actually performing both compression and decompression by the same neural network. And in this network, we also designed the memory token, which is like trying to compress the information and into several like memory tokens. And based on this memory token, we can generate the next level information. So this is what we call the virtual memory tokens. So each segment prepends the read token and appends write token. And the tokens act as the summary vectors bridging the segments, and it scales to arbitrary long conventions without semantic drift. And for the training, we have utilized combined 3 loss functions: the forward compression, like from the like long to short, the compression process, and the backward generation process from short to long, the expansion, and also the cycle, the consistency loss. Well, like from the original, we compressed it to a short one, and from the compressed text, we reconstruct the original context. So we want to minimize the gap between the original and the reconstructed context. So by combining these 3 loss functions, we will train our network with all of them. So we have conducted experiments on different datasets. So basically, we can see that our R3MEM sets new sort of performance across all the 3 datasets, the PG19, Archive, and C4, and compared to many recent new models. And we've shown that the recurrent design beat associative memories like MemReg and so on. We also tested both in-domain and out-of-domain and retrieval. So we found that actually the better compression can lead to better retrieval. And for out-of-domain performance, it is still not good, but the ranking remains consistent across different models. And we also compared like the agentic performance by adding the memory module into an existing agent framework and to see, okay, how the agent's performance will differ by utilizing different types of memories. And we have shown that R3 dominates and due to the superior performance in retrieval accuracy. And we also shown that the implicit memories actually performs better than explicit memories in these experiments. And we performed ablation study to see which design actually is critical to the performance of RCMM. So we found that both hierarchical compression and high quality pairs of the data matters a lot to the performance, and injecting the virtual token into hidden states can improve the performance, but increasing the token length doesn't. And also the backward pass and cycle loss are essential to the performance as well. So to summarize, in this work, we framed the memory as a reversible compression problem, and we designed the R3-MEM neural network, which is an adapter-based reversible transformer with virtual tokens, and we achieved state-of-the-art retention, retrieval, and downstream agent performance, which opens paths to lighter external storage and tighter model memory coupling. And you can find more details in our paper, which has been uploaded to arXiv. So thank you. This is all for today's talk.
Thank you very much, Bang. So this is a period of questions. If you have questions, please go ahead. Yes.
Yes, I do have a question. Very interesting. Actually, I'm working right now using AI agents, and one of the use cases is based on procedural memory. So you do an action, and then you, based on the outcome, you moving to the next action that makes sense. And the idea is, or what we want to achieve is to learn from previous experiments. How will you use your memory to do that?
Okay, yeah. So I think what we're talking about is, I think you consider your memory as a like experience pool, right? Based on the prior experience, how you can better solve the current task. Is this what you mean?
Exactly, yeah.
Yeah. I think if you are saying how we can utilize RCMM for this task, so the idea is, so we designed this architecture for general memory architecture, which means we modeling memory process as a generative process. You have a short query and you generate long context. So if you have like relevant experience stored in the network, basically you can input your the current task description and ask the memory model to output the previous relevant experience. And based on the previous relevant experience, you add it as your context for the current task so that you can see whether your model can better utilize this memory. So as we mentioned in the memory lifecycle, we have both the memory retrieval stage and the memory utilization stage. Well, here, the memory network is served for the retrieval. Basically, you can consider the retrieval is given the query, you generate the relevant memories. And for utilization, you can like add it as a part of a prompt, or maybe perform some analytical reasoning and so on. So there are two different stages.
You mentioned that you use the context, but would it be possible to store into the memory the current state of the world? Because one issue we have is that it's to mimic complex processes, and one step or one question really depend on the previous answers. And it's really hard to memorize that in just the context, because you don't know exactly where in the memory it will go. So
Yes.
Will it be possible to have a memory that internally remember all of the paths that have been already explored, and also then knowing exactly where you are, what are the next questions or action to take?
So if I understand correctly, you're asking how we can like design a memory which can appropriately locate the relevant memory based on the current query.
And remember exactly where we are in terms of process or implementation of the world, because here that kind of memory is more like a long-term memory where you store information for about Bernard Arnault, for example, but not really a short-term memory where you know exactly where you are, and the difficulty is to combine both so that you can leverage previous experience.
So what do you mean by where you are?
Where you are in terms of what you already explore. In our case, it's a sequence of questions and answers about businesses, and so the same question could um, be followed by a lot of different question, um, but it should be specific to what you already learned. For example, if you learn that that business is in Quebec, then the next question will be different than if previously you stated that the business is in Ontario, for example.
I think actually these are two questions. One is about retrieve the relevant information or experience. Another is about reasoning about your current steps. So basically, you can combine a memory module with a reasoning model. So one is just in charge of the retrieve the relevant information based on your query. Another is like reasoning about where we are in the current stage and generate the appropriate queries for the memory network. So in this case, what I'm recommending is instead of relying on a single memory model, either an external RAG module or a memory network, we should combine both a memory model and a reasoning model to solve this task.
Thank you. Again, very interesting.
Thank you.
Okay. Any other questions? Yeah, well, the others think. I have a question about using the GPT to formulate all these framework to renew the memory and so on. Have you thought about not using GPT and trying to manage the memory explicitly by yourself instead of trying to decompose the different blocks by GPT?
So you mean this part generates the
Yes,
context
yes.
query first?
Right.
Yeah. So like the most simple way is we just have the document and we have the subset. For example, you just use original paragraphs from the document and original sentences from paragraphs. But here the problem is like they're exactly the same. So when you generate from long to short, there's no difficulty. From short to long, it's like a text reread expansion. So I think my PhD student, so this work is conducted by my PhD student, Wang Xiaoxiang. I think he has tried both ways, because at the beginning, what we're thinking about is just, okay, let's take the original document and we try to let it to generate the long context given the short query. So it's like we give it the paragraph, let's generate the whole document. But actually this is not aligned with information compression and decompression, because one paragraph just covers a short part of the information of the whole context. So we found that the performance is not as good as asking an advanced language model to generate these compression pairs instead of just taking the original format.
Good. Any other questions? No. Otherwise, we will move to Sébastien. Thank you very much, Yvonne, for your talk.
Thank you, Jimmy. Thank you, everyone.
So we are moving to the second talk by Sébastien Paquet. So the talk is about the agentic AI for the enterprise. So we are going to see the impact of agent in industry. That will be very interesting. Sébastien is Vice President of Machine Learning at COVEO. He has been working for COVEO for 11 years. So he has led a team of machine learning working on cutting-edge machine learning algorithms and so on for search and recommendation applications. So I will not read the whole bio. I think you have access to that bio online. So during those years, Sébastien has worked on different NLP problems and using LLMs for different applications. So I will let Sébastien present the talk, Agentic AI for the enterprise.
Thanks a lot for the introduction. I suppose you see my presentation.
Yes.
It's going to be a really different one. But I want to give you a sense of what's going on within enterprises trying to implement agentic AI. First of all, a small introduction about COVEO. So we provide a relevance for any point of experience within an enterprise. And our objective is to improve the business outcomes of our customers. To make it a little bit more concrete, we have two main lines of businesses. One is for commerce, where we provide product search and product discovery solutions. And the other one is for what we call knowledge. This is where we provide answers generation or search. So being able to retrieve the knowledge within an enterprise and provide it to the end user. All of these are provided by one platform, and COVEO is a SaaS solution. To put it a little bit more concretely, I can give you an example at Dell Technologies where we have implemented COVEO at multiple places, actually. So if I zoom when someone is making a search, we do go into multiple content sources to get the information required. We will generate an answer using retrieval augmented generation approach to have a specific answer to the question. We always cite the sources so that people can go into the document. We can also provide, people also ask questions so that we can guide users in asking more precise questions. We can also provide recommendations. And obviously, we provide search results. So people can always see the detailed search results if they want to see the source of truth for the information provided. So at a big enterprises, and you're going to see the link with Agentic afterwards, but with big enterprises, it's often not one use cases or one website that you're trying to power. You're powering a lot of systems. So at Dell, COVEO is implemented in 25 different use cases. So on Dell.com for the product search, on the support websites, and in the agent consoles, in the chat. So, but enterprises want the same relevancy, the same feeling, the same kind of information available everywhere. So what COVEO is providing is really the connection between all the enterprise content that is scattered around in multiple systems, and also to provide it into multiple experiences at the top. We do that by providing a unified index with hybrid ranking, so both lexical and vector-based semantic search. We have secured connectivity to all enterprise content. So we not only index the content, but we index also the access rights on each document, so that no matter where the information, the query is made, if the user doesn't have access to a document, he will not see it, and he will not see answers generated out of this document. And we provide Agentic APIs and package solutions so that it's easy to integrate within Agentic's frameworks. So if we look at a typical enterprise, you would have enterprise data and content scattered in multiple systems. This will not change. People still want to use the best tool for the, whatever job they're doing. So they're generating content at multiple places within an organization. Most of these systems have access control and access rights, and that need to be provided in at the top multiple different experiences for commerce, on the website, on the help portal, or even internally for intranets or internal tools. And also at the top, these are provided by multiple softwares that are used, and each one of them is a good one for the specific use case. But at the end of the day, you don't want an experience that is disjointed and that you don't see the same information in all these systems, that you don't have access to the same things. So COVEO can securely index all these sources at the bottom and provide a unified relevance that is then accessible within all these touch points. So this is a small introduction to COVEO, but you'll see a link with Agentic AI moving forward. But Agentic AI just re-emphasized the generative AI in general, and then Agentic AI re-emphasized the usefulness of having access to enterprise data in a efficient manner. We go back to the main subject of this presentation, which is Agentic AI. If we look at the enterprises level, Agentic AI is really seen as a breakthrough capability. So it's not a small evolution. It really disrupts, or it has the potential actually to really disrupt multiple workflows or multiple processes within enterprises. So it's something really important, and enterprises are looking at it really seriously. And another quote from Gartner is that they think Agentic AI will be able to resolve 80% of the common customer service without human intervention. So, and this is really important for enterprises where they want to scale and everything, and being able to answer well their customer is really important. And currently it's costly to do it manually. However, that these are all dreams, and but in reality, only half of the organizations are really exploring the use of AI agents. And if you look at the ones that actually have deployed solutions, it's only 12% of them in a recent survey. So people are talking a lot about it. People have a lot of prototypes. People have a lot of ideas on what it can do. But actually, if you look in practice, it's not that used yet. And there's still a lot of issues to make it happen at the enterprise level. And I'm going to talk about some of these issues during this presentation. But if we look at the main use cases where Agentic AI is implemented, if you look at the left, customer service and support is still the main use cases. This is where you want the agent to answer questions or solve problems. Internal operations is also really used use cases, common use cases, because this use case is actually seen as less risky by enterprises. So they test their software with internal operations before going to their end customers. In sales and marketing, we see it more in content generation. So really helping marketing and sales team to generate content, generate emails, generate things like that. So and there's always a human in the loop to validate the generation, but the tools are used throughout the generation part. We see it also in security and fraud detection and other solutions. But if we look at the sectors and the type of companies that are actually using these type of systems, obviously technology and software, they are often the first one to try new technologies, being themselves developing technologies. But even for these companies, we see only 24% of them really implementing AI agents. Then financial services, retail, and customer healthcare. Don't want to go into the full list, but you see that the percentages are actually quite low. And it's even lower if you look at the fact that it's actually enterprises implementing AI agents, not enterprises using them in production. Yes, multiple companies are looking at it, but when you look at the global landscape, it's actually not that many that are rushing to this new technology. But what is agentic AI? I have a slightly different definition, but it's similar to what was just said in the first presentation. But AI agents are systems that can perceive, reason, act, and learn to complete tasks for users. The main thing that is changing from the generative AI systems that we've seen in the last years is the reasoning part. So being able to really understand the issue and act differently or decide on what to do to solve a problem. If we look a little bit more in details of what an enterprise would have to build to have an agent, first you need an LLM model, most probably a reasoner model, so that you can understand the task, decompose the task in subtasks, and then execute each of these subtasks. You would need tools, so either external functions, APIs, other agents to execute these subtasks and get the information required. You would need some kind of instructions. So having an LLM model is not enough. You need instructions to really guide the LLM model and also add some guardrails on how the agent behaves. You don't want to let it go freely within your enterprise. You still want some guardrails, and you want to make sure that it doesn't answer what it shouldn't, and that it actually does what you want it to do. You will need some kind of control loop. So contrary to generative AI solutions where you have a one pass, here, since you have multiple subtasks, since the reasoner model actually need to reason on the output of the first tasks to do the second or third one, you need a control loop to iterate among all the subtasks and to iterate until it achieves the goal. And we just saw it. You need a memory. So expectations are that these agents actually learn from the user experience and past experiences, and that they improve over time. They kind of, otherwise it becomes really cumbersome for humans to interact with these agents if they don't remember what you just told them. So these are the main components you need to build an agent. And I want to contrast also generative AI with agentic AI. I've been talking about it a little, but generative AI systems are a little bit more reactive systems. So you normally have a static execution plan, you have limited adaptability, But at the same time, which is beneficial actually for enterprises, you have more control and predictable outputs. So for generative AI, you would, for example, do a question answering system. You have one question, you do one retrieval step, you do the generation afterwards, and that's it. So the model will do exactly the same thing for each query. The only thing that will change is actually what information is retrieved to generate the answer. So it's less flexible, but at the same time more controlled and predictable. So there are advantages also with it. And on agentic AI's part, you have an autonomous system, which is more intent-driven and can adjust its plan. And also that may do multi-step resolution. It's really could be more powerful, can do more things, but at the same time, you're losing control and it's really less predictable to have such a system. You see the contrast because within enterprises, it will add some constraints on how to actually deploy these systems. So now let's talk about the agentic AI within the enterprise. I'll just start with a myth. So people often start with reading blogs and articles, and oftentimes published by the ones who are providing the agentic framework. And you can easily, after reading some marketing blogs saying that our agents can do it all, and then you actually prototype and you see, oh, it's really fast to have a first agent in place. You do a small POC. Most of the time, you will copy your data. So you will see, oh, I have this small data set. I want to try it on. Um, I have these small examples I want to try. And you can have really positive feedback. You have a small POC that's working. So you're really enthusiastic and say, oh, it's really promising. Then you say, okay, I want to scale it and deploy it at my enterprise, and then you will hit a lot of red tape and walls. Enterprise security concerns being one, hallucinated outputs. It's still an issue to have one LLM hallucinate. So think about an agentic system with 10 prompts. Each one of them can hallucinate. It will be really hard for the people developing the solution to guarantee to their security teams that the model will not do something that it shouldn't, or the agentic system will not do something that it shouldn't. And also just integrating within the enterprise system is not that easy. You need to get information from different systems. You need to integrate the solution within the enterprise applications, and that can be more complex than anticipated. So often we see that multiple prototypes get archived. Too costly, too long, not good enough. And most of the times these prototypes are not done in collaboration with the full company or knowing what the others are doing. Most of the time you have multiple prototypes in parallel done by different teams, all of them trying to reinvent the world and redo the full stack from user input to data access. You often see enterprises at some point saying, okay, I have invested in multiple prototypes. None of them are that useful. It's really costly. So I'm going to wait and see if the agentic framework get a little bit better and more enterprise ready before we move even further with that. I think this could be a mistake, actually. You do have, as I said at the beginning, it's really something that will be transformative. So you need to set up your enterprises to work with these kind of systems. But doing prototypes is really good, but you need to know that these are prototypes, and trying to scale them to production one by one is not necessarily the best approach within an enterprise. So if I summarize a little bit, the common scenario we're seeing is that We have a team experimenting with prompting large language model. Everyone has access to them, quite easy to do. Results feel promising, like I just said, and they think they're close to a production solution. But then it becomes clear that critical elements are missing. Prompt consistency. So anyone who work with prompts actually it's really easy to do a one-liner prompt, but if you want to do an enterprise prompt that is resilient, that will still provide good outputs, even if the inputs are strange or people are trying to break your system, it's really hard. You need to ground your agents within your enterprise content. That may become complex if you wanted to do it, if you need to do it securely, respecting the access rights for the information. Evaluating the quality of a solution is really hard. It's so flexible, can generate so much stuff. It's not easy to have evaluations to really be sure that you will maintain a high quality for all use cases. So and goes and on and on and on. So there's multiple things required to actually have the systems in production. Typical obstacles are inconsistent prompt design. So you need a strong prompt engineering practice, so to be able to test, to version your prompts, to make sure that you've tested it in multiple situations. You need also to test it against attacks on your systems. So not only the happy path, but users that try to make your agent generate something it shouldn't. Which actually highlights the lack of evaluation frameworks. And this is something I think in the academia, if you can figure out a way to evaluate agentic systems and do it consistently and autonomously, that will be really valuable for enterprises. But building evaluation frameworks is really hard. And that is actually really important, actually. And there's no enterprise mechanism to ground the responses sometimes. So yes, you can have MCP servers, and now we see multiple MCP servers for a single application. Actually, many applications are coming up with the MCP servers. But you need to realize that enterprises will have tens of systems. And if you do one MCP server per instance, then you go back 20 years in search to federated search, and you ask your LLM actually to rank the results and to decide which information is useful. And they're not that efficient actually to do that. It's really important within enterprise, and this can slow down a lot of projects. So what's the reality for enterprise? There's hundreds of siloed systems to manage and contain. There's terabytes of data. For some use cases, we might say gigabytes, but if you want to support a full enterprise, you will end up in terabytes. Most data sources are secured with complex access rights. So you cannot just copy the data into your warehouse, or you cannot just extract the data from the system. And these data sources actually are live. So there's always new content. So you cannot just copy the data. You need to index both the content and the security. The current pace of change and innovation is constant, and actually for enterprises, almost unsustainable. There's new LLMs every week now, almost. Even for the LLMs that are available, suppliers are removing or deprecating the API really fast. within less than a year most of the time. So it's really hard. You're always prompt engineering, redoing your prompt engineering, redoing your evaluations, redoing because you need to keep up with all these changes. So this is really hard to follow for enterprises. And yes, you may have on-premise open source models, but for many use cases, you don't have the same quality, and you're kind of losing on this space of innovation because yes, it's going really fast, but you want to have the best solution out there for your enterprise. So you need to figure out a way to keep up, actually. I've said it a little, but prompting is hard for enterprise-grade applications. You will need multiple prompts. You will need to work a lot on your prompt evaluation, on your prompt optimization. It's not the simple ChatGPT prompt you're doing yourself for simple tasks. And most of the time, your AI and Agentic AI solutions need to be deployed in multiple applications. So again, you have to figure out a way to scale your applications. So the reality for AI agents within enterprises is that it's not a silver bullet. So my first comment is, do you really need it? It's really a new technology, so enterprises should expect changes. So build their solution knowing that each component should be easily replaceable. It's not that obvious to do, but I think it would pay moving forward. These systems are non-deterministic. So, and if you add non-deterministic system on top of each other, the more you add, the more you compound the hallucinations and the probability that something goes wrong with the system. Rapid development is possible, and it's really useful to validate your ideas. But you also need at the same time to think about enterprise grade and your enterprise infrastructure so that the system you're building on is actually solid and you have a solid foundation for it. Don't minimize the effort required to maintain and control the system. If you don't think about it when you're building the system, then you're going to be blocked by the compliance or security team at some point because they will ask some level of control and guarantees that the system will perform right. You need to integrate within the infrastructure, within the other systems. And most of the time you need access to enterprise knowledge. So most useful use cases, you said that the main use cases were about support, were about internal use cases. These use cases all required enterprise knowledge to work well. One thing that people minimize is how brittle are prompts. They are really fragile, and you can just tweak them a little, change a word, retweak them. Sometimes you just add a return at the end of a line, and it changes the output. So prompts are really fragile, which is not good within enterprises. To support. Even if you're good with GPT 4.0 and now you have GPT 4.1, you will need to redo your prompt engineering. You will need to. So the evolution of software is really hard because each time you change a model, even if you stay with the same model but just upgrade the version, the outputs will change. The prompt you did will not be the best one anymore. So you will need to redo the prompt engineering process. And in production, this is really problematic because this brittleness can break your downstream workflows auditing compliance. So it's really important to tackle this issue. So like I said, new prompt engineering and evaluation is required for every model release. It's really cumbersome to do. I think it's still a good research field to figure out how to do it efficiently. And also, if you add that you have to do it every 6 months, then ideally you're able to build an automated prompt evaluation and tuning system. So ideally you're able to have a strong enough evaluation framework that you can rerun it automatically and that you can automatically adjust the prompts. But again, a lot of research is required to really automate that. But they are interesting research done and interesting things you can do with LLMs to use LLMs to improve the other LLMs prompt. But again, it's a lot of moving pieces and a lot of probabilistic outputs. But stacking a strong evaluation framework and being able to automate the prompt tuning, and this is something that will make your system more sustainable over time, will mature, and that you will not be that much impacted each time a supplier changes or deprecates an API and gives you another one. So what about more specifically about agentic AI prompts? Just remember that agentic AI system is really different than just ad hoc user inputs in chat tools. It really requires to think carefully about how you engineer the prompts because they need an enterprises to be robust, repeatable, optimized for whatever task you want to give it. It's you're going to spend most of your time trying to optimize these prompts. And the complexity is even greater when you dynamically assemble these systems. You can see it with MCP servers, where you can describe multiple MCP servers and you have your MCP client that can decide which one to use and things like that. This is an example, but each one of them needs to be really well crafted actually to work well within enterprises. So what are the best practices in this context? Modularize your prompts in discrete tasks. So don't try to do one prompt that does 4 things. It's better to do simpler tasks, something that you can control better, something that you can evaluate more easily. Then you can chain them, but do the chaining intentionally. So make sure that the sequence makes sense, that the inputs of one builds on the outputs of the other. Ground your prompts in your enterprise knowledge so that the information is factual. This was true for generative AI. It's just still true for agentic AI. But the important part is that once you've done, you're not done at all. So you need to continuously audit. You need to version your prompts. You need to monitor the performance of the system. You have so many moving pieces in place that you need to invest in monitoring the system properly. So you need a really strong evaluation framework to validate that the agent outputs are continue to be good over time. And that each something layer behaves as expected. So how to avoid the trap of a solution in search of a problem? Because we've seen that, it's like we've seen customers, I want to use agentic AI to do what? I don't know, but I want to use it. It's like, okay, but you're doing in reverse. So first understand your business need. What problem do you really need to solve? What use cases, pain points do you need to solve for? And assess whether the solution you're building is real and mature. So there's a lot of startups. There's a lot of new open source libraries. There's a lot of models. Make sure that you're building on strong grounds. Consider really soon in your process how you're going to monitor, evaluate, and control. It's really important. It's not an afterthought. It's something you should think about from the start. Do you know where your enterprise data is? Do you have access to it? Can you use it within your agents? But as I said, agentic AI is not a silver bullet for everything. What are the advantages compared to existing solutions? Are you simply replacing a simple create button with a full agent flow to create it automatically? It's like, okay, you're adding a lot of complexity for something that was actually really simple to start with. So do you really need an orchestrator calling multiple systems? For this to be valuable, you need to have a really strong ROI. So you need to get a lot of value from having such a complex system, because you're gonna have to manage change with your teams, with the different systems, and at some point, someone within your organization will ask for the ROI. Will ask, okay, we invested that much, so what's our gain out of it? Because if you look at enterprises, you will end up probably with multiple agents at some point. So if we say that they are going to revolutionize the enterprises, then you're going to have multiple agents at some point. Each one of them will need to be built on strong ground, will need to respect your enterprise compliance. So, and most of them will actually, to be useful, need your enterprise knowledge. So one way to look at it is to get started with focusing on the foundations. We've seen a lot of people start with the multi-agent system prototypes. That's good. That's to validate the approach, validate what you want to do with them. But at the same time, as you have teams trying prototypes with different multi-agent or single agent systems, you need some teams in your organization trying to answer the bottom question. So is your enterprise data securely accessible? Can you find relevant information? Already starting at step 2, you already have value out of your system because people can actually find your information. Then if you don't need agentic solutions and you simply need a generative AI solution, then you should do it. Don't complexify the system if you don't need to. But if you have not even played with LLMs yet and you have not even a generative AI solution, jumping to agentic systems might be a big step. So maybe you can try with understanding, working with one system that is more controllable, where you're going to feel the prompt brittleness I was talking about. You will see one prompt, one LLM behaves. Then if you have a good use case for a single agent, maybe start with one. Make sure that you can have a strong system, that you understand the reasoning part, that you understand the work decomposition that is going on, that you can control, evaluate what's going on. And then once you're ready and you have multiple single agents, you can try to put all of them within one multi-agent system. And this is kind of strange for me because multi-agent systems is really new in the news. It's like the last months. But actually, I do have a PhD in multi-agent systems that I completed in 2006. But at that time, it was really, really, really not at the level where it is today. But it's nice to see that same ideas are coming to fruition. But this is actually how I see it in an enterprise. If you want to have success, if you're the teams building prototypes at the top, make sure that the teams that are building the foundations will actually connect with you at some point. And if you are the teams responsible for the bottom part, make sure that you build it so that they can be used and power agentic solutions. If you look more precisely at the different agentic framework out there, there's multiple of them. You have ones from OpenAI, Amazon, Microsoft, Salesforce. You have more open protocol like MCP, Model Context Protocol. But at the end of the day, within one enterprise, you're going to have multiple agentic solutions. Just because Salesforce have their ecosystem, they will have their Agentforce system in there. Microsoft have Microsoft 365, they will have their agent in there. The same for all the big players out there. And most enterprises are using all these services. And all these services are talking different languages. Yes, their MCP is slowly becoming, or actually quite fast, but it's becoming a standard. But it's not currently that well supported by all the platforms. So now I'm going to switch a little bit, but for COVEO, I think it's a nice way to be able to plug within all these, to plug your enterprise knowledge within all these Agentic AI solutions. We do provide things like MCP server, agent force actions, and all the connectivity to all these agentic platforms. So this is a way to do the retrieval part more easily. Because it can be really cumbersome to do it for each one of these agents. But once you have the foundation ready, then it's really easy to spawn multiple of these agentic AI solutions. So what COVEO provides to help, so relevance generative answering. So if you have only need answers, then we can provide it directly. You don't have to manage the prompt. You don't have to manage the prompt updates. You don't have to manage the model updates. We do it for you. If you have a chat copilot or any of the agentic systems I shown, but you still don't want to manage the prompt to answer questions, we do have the Answer API that can be easily integrated within these Copilot applications. And if you want full control, then we can return you the passage retrieval. So we return the raw text to your agent, but we return it for a specific query. So really fast to do passage retrieval, sub-second level passage retrieval, and then your agent can be grounded with this information. So in conclusion, Agentic AI is really promising. I think it will revolutionize a lot of what we do. It's still really new and evolves really fast. So whatever you're doing, make sure that you're not building it on things that will not be there in 6 months, or make sure that you're thinking carefully on how you build these things. There's multiple challenges. I've listed a lot of them in this presentation to implement it within the enterprises. So there's still a lot of work to do. I think yes, we've talked about how to better generate and better have agentic, and I see a lot of people working on trying to have agents that work well together. But evaluations is necessary and actually really hard to do with these type of systems. And this is really valuable work for enterprises. And the enterprise data is important, but you don't need to reinvent search. Yes, connecting to a source is something, be able to copy the data to a source is something, but doing a full enterprise ready search solution is not that easy. And again, it's an error we've seen with many of even our customers trying to rebuild it internally, and most of them fail at some point, just to be able to scale it to the full scale of their enterprise. So thanks a lot. This is what I had. I hope it gives you a little bit more insights of how it's going on within the enterprise, and of course, kind of my point of view here. I don't see everything going on within enterprises, but thanks a lot. Any questions?
Yeah. So that's a very interesting talk, and this put in contrast with the first talk. So we have the agent technologies from research perspective, and now you offered a industrial perspective, and very interesting. Yes, questions?
Yeah, very interesting topic. One question related to your indexing the accesses. If you have a large data set and you want to, and you have a large team accessing those data, and you index all of those accesses to the data, if the team is constantly changing, doesn't it add an overload in re-indexing everything to that large corpus of data when new members adds or removes? How did you address that part?
Yeah, and yes, people are added, removed, and also groups are created and removed, groups of users. The system is actually done to re-index the access rights. So we don't re-index the full document when only the access rights changed. So we re-index the access rights themselves, and it's a real-time. It's a process that is done really frequently. So there's no big secret there, but you just need to re-index the security really often, actually, to keep up with the enterprise access rights.
So that access is not coupled with the data itself. So each data that has been indexed or vectorized, it doesn't have extra field of access into it.
The security is indexed separately from the document, and it's linked to the document. And at query time, we validate that the user has access to the document before returning the documents.
Okay, great. Thank you.
Laurent?
Yeah, I do have a comment and a question. First, I got my PhD in multi-agent system like yourself, but in '96, so 10 years prior.
Yeah.
And what's fascinating is that the core concept, autonomy, etc., didn't change since.
Didn't change at all. I could have used the same picture I used in the courses at the university in 2005.
In '96 or even before.
Yeah.
What changed everything is the LLMs. LLMs can make those concepts reality. So it's fascinating for me, and I guess for you too. So my question is, do you have any successful use cases of Agentic AI implemented in production already?
Full agentic AI systems, I've seen more prototypes than real production. We do have a lot of production deployments of generative AI solutions for generative answering, and this is already really valuable. Full agentic systems, currently I've only seen prototypes done by our customers, and so we see chat. So it depends on your definition of agentic systems. We see many chat. So we have customers that just started with a chat flow that they're controlling more, but they are adding generative answers, and they are adding things within a chat, but it's still a chat flow without a reasoner model in it. So I don't see it a lot, and the statistics I had on a recent survey was 12%. I've not seen the 12% in person.
And from the prototypes, what will be the most promising, do you think?
It really depends on different customers. I think the one promising one is actually a similar one to the deep research functionality that you have from Perplexity, from everyone, actually, OpenAI, Perplexity, and everything, but done for the enterprise. So being able to have an agent that will actually understand a more complex question that requires multiple retrievals and that requires more reasoning. This is one that I see really good prototypes and close to being able to use that in production. Others are when you control an API or you do something specific for an API. So having agentic solutions for accessing Jira systems, so issues and things like that. So getting the issue. So I've seen prototypes trying to just get the issue from Jira directly and then ask an LLM to actually code the fix. So these kind of interactions. In production, what we see a lot, and I'm just thinking about it, is coding agents. This is used in production. This is more product, I would say. But yeah, this is what I've seen.
Actually, I'm currently working on a kind of deep research AI agent. So yeah, I agree.
Yeah.
Very promising.
Good.
Thank you very much.
Yeah, as both of you have done PhD on agents some time ago, what's the main
It was
difference?
popular at the end of the millennium.
Yes, it is. It was very popular. Now,
Yeah.
as you mentioned, Laurent, you mentioned that the difference is that we have LLM now, and certainly we have a better understanding of language and possibly more reasoning ability by those LLMs. But at the time when it was about the 2000, when agent technologies was proposed, we talked about a lot of protocols between different agents, and those protocols are well designed. So you have to react in some manner to make that result understandable by other agents, so that other agents can plan for the next actions. I think we didn't see a lot of follow-up later on of that technology. What do you think about the current LLM-based agents? Do we have the similar risks of failure in several years? I don't know. What's your input about that?
It's a great question. I don't have. I'm not sure I can predict the future that well, but I
But do
think
you
at
see
this
the same
point,
weaknesses?
yeah. But I think now that we have reasoners, so the reasoning part of the agent is less just heuristics or static functions. I think it's more, I see more possibilities, and we already see it. We already see good examples with coding agents and things like that, and deep research agents. And so we already see good examples that work, that solve a problem that is really useful in real life. So I think right now it's more advanced than it was before. I think it was still a lot in myself. It was a lot about small tools that are not really applicable in real life, but we were playing with different agents. But now we do have real problems that are solved. As for the communication problem, MCP is starting to become a standard. It's not that well defined if you compare it to the communication protocols we had at the time, meaning that it's really open, really free. It's good because you don't have much to do. What changes is that you can simply describe your API with language, with English language. So kind of easy to describe, but at the same time, it's not that precise. So it's good if you have agents that are really different with really different descriptions. But if you have multiple agents that have similar descriptions, then it's harder for the client to figure out which ones to use when. So I think there's still a lot of work to do to improve MCP and to make it enterprise ready with authentication, security, and everything. But we see a lot of work and all the big companies starting to be behind it, so it will move fast.
And to answer to your question, there is always a risk that hype technology will not deliver. But from what I see on experiments, there is already really promising results. Like we talk about kind of deep research um, tools. Also, for me, it's a natural evolution of Gen AI/LLMs. It's a way to, because you have different levels of agentic AI, more or less control. And so you name it the way you want, but it's the natural evolution of LLMs. So for me, there is no doubt that it will be used in real life. To which extent, to real multi-agent systems that can do some auto control, etc. I don't know, or maybe when, I don't know, but. For me, it will not go back into the dark age of
Okay.
I will have to go shortly, and I see one raised hand.
We have the last question. If you have time to answer that, I know you have to leave in 1 minute. Armstrong, last question.
Okay, thank you so much. Yes, my question is about the use of LLMs or agents in the industry-ready problems. We have this challenge in industry where legacy systems are always preferred to a fast-moving systems. We have seen this in most industries. And I don't know when in the context where industry will be building agents on LLMs, and we have seen many more types of models will be coming in the future, which were not LLM based. The agents will be changing frameworks, the constant moving parts for industry. How is it ready? How is the industry ready to adapt to these fast moving changes as opposed to the legacy system that has proven some resilience and stability over time? Thank you.
That's a really good question, and actually, it's I don't think most enterprises, I don't think they're ready for that fast pace of innovation, fast pace of changes, and I see more promises in these legacy system integrating within their already available services, but just improving them with generative AI, than a completely disruptive system for an enterprise. So, for example, you have a CRM with Salesforce. I don't see a small startup replacing Salesforce at an enterprise, but I see Salesforce adding generative and agentic AI capabilities within their offering. Because you still have the stability of the existing system, but you just add features on top of it. But it's a really bigger leap if you want to replace it all and say, okay, I don't need it anymore. I have an agent that answers my customers. That's a really bigger leap to do.
Good. Thank you very much. I know that Sébastien, you have to go. Thank you for both presentations. That's very interesting. So let's conclude here. And well, we will have very soon news from the CLIQ-ai platform. So hopefully we'll soon run it normally, and we are really in the last phase to set up the projects. So stay tuned for that. Thank you very much for all. So we'll close here.
Thank you. Bye.
Bye bye.